All right, guys. Today, what we're going to do is we're going to talk about astrology. So I know this was one of the questions that folks had when we first started talking about this course. Is that too much? Might be too much. We'll do that. We started talking about the course was, what's the difference between astrology and astronomy? Because you hear those two words. They both got an ology, which is very sciencey. The truth is, astrology is a pseudoscience. It's not a real science. Astronomy is a real science. So that's why you're in astronomy class, not astrology class. But we're going to play around with this a little bit, kind of in our effort to understand what actually constitutes science and what does not constitute science. Anybody a Calvin Hobbes fan? No, nobody even knows. Your mom was? Oh, I do too. It was like my all-time favorite comic strip. Like, I'm not sure how well it's weathered time, but Bill Watterson, oh my goodness, like I have all the comic books as well. And every morning I would wake up, the only thing I wanted to do is read the paper to read the next Calvin and Hobbes. It's just so funny. But it's kind of quirky. It's about a stuffed tiger who's basically named after the famous philosopher Hobbes. And this young kid, Calvin, who's just a goofy little troublemaker who pretty much was basically just like me when I was a kid. But anyway, we're going to talk about the stars today. So we're going to try and understand what astrology is, and I am definitely not the most qualified person to explain this, so I'm going to do my best, okay? So after great research upon the internets, the way astrology is supposed to operate is that when you're born, there is a particular alignment with where the sun is in the sky and where the earth is. And basically, the part of the zodiac that is facing the earth, which you wouldn't see because of the daytime anyway, somehow sends these like deep space energy signals to you in the womb when you're being born, and then it somehow causes you to have a certain type of life. Like some bogus like it predetermines like what's going to happen to you. It's an awful lot like a fortune cookie, which
I seemingly display a lot of Aquarius traits, and I am an Aquarius, but I still mostly consider it bogus.
So we're going to see today. We're going to see today what we are, and we're going to have a little bit of fun with this. But yeah, it's kind of a lot like a fortune cookie in a way. But that's about the best I can do to try and explain this. But they do use real constellations, like the constellations we're going to talk about are things that are named by astronomers. But remember, like astronomy dates way back. In fact, it might be the oldest science of all, because people wanted to study the stars to understand the seasons, to understand when to plant the crops, when to harvest the crops, things like that. It was a very important thing. And of course, dating back to even magico sort of religious sort of things of, it's auspicious to be born on this star date versus this date and all these other things. Like it's been a very important part of human society for a long time. So it might have led its way kind of into just the reason we developed science to begin with, was to understand things like weather patterns and climate and the seasons and things like that. So it's kind of interesting in that regard. But we're going to try and put astrology to the test today as best as we can. In order to do that, we have to understand the signs a little bit. So I did my best. I looked at a lot of sites. There's a lot of conflicting opinions as to what these different signs in astrology mean. So exactly. I had to choose somebody to help me, and I picked Hello Kitty. So Hello Kitty is going to help us to understand what the signs are, and we'll see what we've got here. So we'll roll through them. So just for fun, first off, we've got Aries. Oh, yeah. Do you have any Aries in here? March 21st to April 19th? Oh, yeah. I'm an Aries. I'm an Aries too. John, do you find yourself impulsive? Yeah. Energetic? Yeah? Fiery? No. Okay, what else do we have here? We've got the Taurus, the bull. Any Tauri here? No Taurus? April 20th to May 20th? No? So patient, stubborn, loyal. Oh. Think to yourself, while I'm kind of telling you about these, which of these characteristics would maybe be useful? Which of these would be useful to be if you were going to say, for instance, be president? Ooh, think about that one, okay? Because that's how we're going to test this. Gemini, May 21st to June 21st. No Geminids here? No, Gemini, no. The Geminids are the meteor shower, right? Because it comes out of that region of the sky. So versatile, outspoken, curious. Do you guys not know when you're born? How about Cancer, the crab? All right, not Cancer, the bad Cancer. This is Cancer, the crab. Okay, so yeah, we've got a couple. Do these describe you? Nurturing, yeah? Insightful, sensitive. Yeah, so like, do you kind of notice a pattern here? Like a lot of these things are like, oh yeah, I like that. I kind of like to want to be that, right? I like to be like insightful and nurturing. Like, so a lot of these things are like the horoscope that's read in the paper. There's always some part of it that you can kind of feel like, oh, well, yeah, sure, right? Notice how kind of vague they are. Leos, any Leos? Oh, there we go. Opinionated? Confident? Proud? Not anything you want to admit. How about Virgo? Virgo, all right. Intelligent? You're going to take it. I'd take it. Yeah. Introverted? Do you guys know what introverted means? So it means like really keep to yourself, like doesn't like to be around other people, like just kind of steps back from everything. Perceptive, picking up on stuff the rest of us are missing. How about Libra? Libra, September 23rd to October 23rd. Caring, indecisive, fair. I like how there's always like two pretty decent ones and then one that you're like, I don't really like that one as much. Right? I'm going to give that one up. Notice how they do that? Scorpio. All right. Persuasive. You convince people to do things they don't want to do all the time. Like, hey, everybody's doing it. Resourceful and secretive. Yeah, maybe. I'm not going to tell. How about Sagittarius? Yeah, no Sagittarii here. Philosophical, knowledgeable, honest. Right. Capricorns. No Capricorns, December 22nd to January 19th. Practical, ambitious, efficient. Aquarius. Aquarius. Oh, both of you guys. Okay. Humanitarian, like care about doing good works for other people. Visionary, like big broad picture people. How about eccentric?
Well, that's certainly one way to describe me. Although personally, I actually work for the term a smidge off my rocker.
Okay, well, we won't say that. So, eccentric's a funny word. Basically, it kind of means. I have a hard time describing eccentric. Eccentric's a description of a person that sort of does things in a weird fashion, even though they don't necessarily have to. Right? They're just kind of insistent on doing something in sort of a real strange way. Usually, oftentimes, you hear it applied to people who happen to be like really wealthy, so they can do things however they want to do them. Like the rest of us wouldn't even consider doing it that way. I've got a very eccentric friend. He's a very odd guy. His family owns a lake, and it's huge. It's like at least a quarter of the size of Lake Monroe. It's humongous. It's in upstate New York. They're filthy rich. Their great-great-grandfather used to sell snake oil, like these vials of food coloring and like weird stuff mixed in it to cure everything, like out of the back of a wagon, right? And he made millions. Like he's like filthy rich, and he bought this entire humongous property in upstate New York way back in the day when people drove around horses and buggies and whatnot. Bequeathed it to his family, and so every family that's part of this big family group owns their own big like wilderness chalet like on the side of this lake. The only way to really get there if you don't want to drive for like 18 hours is to fly in via float plane. So they all have planes and they land them on this lake, right? They used to have my wife and I come up to teach wilderness skills to everybody in their family, like their kids and everything. And so we'd like run this big program and do a bunch of fun stuff with them. But my buddy is like, he's super eccentric about things. Like he's the definition of it. Because he's got so much money, doesn't matter how he does things or what he wants to do. Like he can just do it that way. And the rest of us would be like, what? It's like makes his own like whipped cream. He won't eat store-bought whipped cream. It has to be handmade and hand whipped. He won't touch it. Otherwise, it's like poison. He can't have it. It's like toxic, right? Doesn't matter how much sugar he puts in it. Just it has to be handmade. Like all sorts of really weird little things like that, where the rest of us would be like, hey, go to the grocery store and just get somebody, you know, don't really worry about it. But yeah, all sorts of weird stuff, you know, like flying in on a float plane, you know, things like that. But anyway, eccentric, it's a pretty funny one. I like how you guys are finding some of these describe you, some of them don't. Pisces, the fish. No Pisces? Giving, spiritual, dreamy. Now we're slipping away from science class, aren't we? So what we could do is we could ask ourselves which one of these groups would be best suited to be president. And rather than try and guess myself, I went online and I looked up every astrology website I could find. I spent like way too much time doing this. Afterwards, I felt like kind of stupid after I had done it. And I wrote down a whole list of every type of a star sign that they recommended would be suitable to be president. And I basically came up with two options. And of those, one was really more promising than the other. The first one was Leos. And a lot of people said, a lot of these astrologer folks said, they're well suited to be managers, architects, inventors, teachers, athletes, and presidents. I missed the boat on that one. So what we're going to try and do, looking at Leos, is we're going to see just how often a president has been a Leo. Okay, so in order to do that, I gave you a list of every single president, including the most recent one. I have to update this every 4 years. And their birthdays, so you're going to use this information right here to jot down kind of by them what they are. So if they're like a November through December, jot down Sag by them, and then we're going to add up the numbers on our paper. So take a second, I'm going to leave that up, and you guys can go ahead and jot those down. Try and... Okay, so based on my detailed research into astrology, determined that Leo should be the most common president. So we're going to try and sort that out here. And I made these little lines here because we're going to put two different things in the columns. So Aries, how many did you guys get for Aries? I got 2, and you guys got 2 back there? I'm going to say it's 2. It's kind of hard to do. How about Taurus? 4. What about Gemini? 3. Cancer? Okay. Leos. Uh-oh. Leo's looking awfully average here. Virgo. 2. What about Libras? 4. Scorpios. Wow. Sagittarius? 3. Capricorn? 4. In Aquarius? 5. And then 4 for Pisces? Okay, yep, that's exactly what I got. Yeah, this one here is a bit troublesome. President Biden threw us over the edge there on that one. So let's take a look at this data here and try and decide like just how different does the data need to be to really show a true difference in what's going on here. Like how much of a value of a difference would you need to see to be able to say, hey, like Leos are more likely to be president than another sign. Okay, like we're going to try and take a look at that. So let's just jot down here which ones had the largest number of presidents and how many. Well, that was Scorpio. Sorry, Leo. Scorpio had 6. The smallest numbers were, well, both Aries and Virgo. At only 2. Looks like I'm never going to be president. So looking at your results, science is about discovering patterns in nature. It's really what it's core fundamentally about. Do you see specific patterns that jump out, or does the data look pretty similar? What do you think? It really does look pretty average, doesn't it? Like it looks pretty similar. Yeah, we've got some low ones here, and we've got one that's a little bit higher, but overall, they're kind of falling right around 4, 5, 3, 4, 5, maybe a 6. 2. Like they seem to be pretty evenly spread, don't they? So the question we're essentially asking is,
you know, in a random smattering of people in the United States, like there should be kind of a random amount of people that are chosen to be president from each of the signs, unless astrology really works out. And if you happen to be a Leo, you're way more likely. Well, that obviously doesn't work, right? Just without even analyzing our data at all. So really, I'm going to put we don't really see patterns here. Maybe Scorpio is a little standout, but there's really not patterns. Next, we're going to do something that's a little tricksy. We're going to calculate standard deviation. Ooh. We won't do this like ever again in here, so don't fret, okay? The only reason I want to do it is to show you why your statistics classes are useful. If you have parents or know somebody that works at Cummins, they probably use standard deviation sometimes, depending on what they're doing, because they have to know things like, what are the tolerances of the part that I'm making? How close does it have to be to these actual measurements? How far can I be off and it won't break the engine, it'll still work? So they look at standard deviation quite a bit, and there's many different ways to measure standard deviation and do statistics. We're just going to do one that's pretty simple, just so you can kind of see how it applies to data. But really, anytime as a scientist that you present something, you have to show things like the standard deviation. You have to look at the statistical probability that your results really do show something. Because let's be honest, sometimes in astronomy, we're looking at numbers that are crazy huge or crazy small. Is your experiment showing that there's enough of a difference in what you discovered for it to really be a discovery, or is it just random background noise? That's really what a lot of science boils down to when you're looking at stuff like cosmology. So we're going to calculate standard deviation on the back. Woo. And I put a whole description on here. It's probably overdone, but I'm going to read it to you. So, here we go. In statistics and probability theory, standard deviation represented by the Greek letter sigma, shows how much variation and dispersion exists from the average or mean or expected value. A low standard deviation indicates that the data points tend to be very close to the average, the mean. High deviation indicates that the data points are spread out over a large range of values. The standard deviation of a data set is the square root of its variance. Some big words here. A useful property of standard deviation is that, unlike variance, it's expressed in the same units as the data. So our data happens to be star signs and presidents, or basically presidents per star sign is our data. In addition to expressing the variability of a population, standard deviation is commonly used to measure confidence in statistical conclusions. In science, researchers commonly report the standard deviation of experimental data, and only effects that fall far outside the range of standard deviation are considered statistically significant. Normal random error or variation in the measurements is in this way distinguished from causal variation, like real true causes of the variation. For a finite set of numbers, the standard deviation is found by taking the square root of the average of the squared differences of the values from their average value. That was a lot of wordage there. For example, considering a population of the following 8 values. Okay, so there's 8 values here, just like we had a bunch of values for our different star signs for presidents. They would have the average of 5. You'd add them all up and divide by how many there were. There were 8, we'd get 5. So let's go ahead and rock that out for our presidents in our signs. Okay. How many presidents do we have on the front there? 40 what? 45? Okay. We got 45 presidents. Okay. How many different signs do we have? 12. Okay. So on average, how many presidents per sign should we have? Well, we're just going to divide. Some super complicated math here. 45 divided by 12 equals 3.75. Okay. Since we can't have 0.75 of a president, at least last time I checked, or 0.75 of a sign. We're just going to go ahead and round to 4 per sign. That's what we just determined. So on average, if this is just kind of random distribution of people that become president, there ought to be about 4 on average. And glancing at the data, I do have, there's an awful lot of 4s in there, isn't there? 1, 2, 3, 4, 5, 6. The mode is definitely 4, I think. Just glancing at that. That's a very, very common number. So right away we're like, uh-oh. Like, it seems like our data really doesn't show anything at all. But let's carry this to fruition just for the heck of it, because we're having fun with math. So to calculate the population standard deviation, we've got to first compute the difference of each data point from the mean, the average we just came up with here, and then square the result of each. Okay, it sounds scary. It's really pretty easy. I did that for this data set here. So let's do it for our 4 presidents per sign. That's why I gave you an extra column here. And what we're going to do here is in these boxes, I'll write this so I know what I'm doing here. I'm going to do the difference from the mean squared. So let's see how that works. I'm going to take my mean, my average there was 4, right? So I'm going to take 2 Aries minus 4, which was my average, equals -2. And now I have to square that, which is x2 key on my calculator. And I get 4. Okay. So now that I've got that, I'm going to cheat a little bit. In any place that I've got a 2, I'm going to go ahead and write a 4 so I don't have to redo it. Okay. Now, you can do this in your head, but 4 minus 4, right, is 0. If you take the square of 0, you get 0. So any that say 4 are going to be 0. See how easy math is? Let's try that with 3. Well, you probably know that 3 minus 4 is -1. If you take the square of -1, you get 1. So all the 3's come out to 1. Let's do 6. 6 minus 4 is 2. Square that, you get 4. How about 5? 5 minus 4 is, of course, 1. If you square that, you get 1. Ta-da! Some really complicated math there, right? A lot of big words to describe something that's actually pretty simple. Okay? But you can see what you're doing here. So these values are the difference from the average squared. Now let's flip back. Next, we're going to compute the average of all those values we just got and take the square root. Okay? So we're going to average all these numbers we just got and square root it. So in order to do that, that's going to be the square root, I'll just write it here, of, we need to know what the average of all those numbers are, so I got to add those up again, don't I? So rather than push all these buttons on my calculator, right, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I've got 15 of those, okay, divided by, how many star signs do I have? 1, 2, 3, 4, 5, 6. I've got 12 of them. So I'm going to have, 15 divided by 12. This is my number of signs. Okay, this is to get my average. So on my calculator, take 15, divide by 12. Well, that didn't want to work. Okay, and then I need to square root that, which on my calculator is a shift. There we go. And I get 0.89, which I'm just going to go ahead and round, equals 1. Okay, this is 1. So my standard deviation, if I was going to write this in sigma here, which is, I'm not really good at writing sigma, I said here, the quantity of the population standard deviation, this quantity is the population standard deviation, and is equal to the square root of the variance. Thus, if our average was 5 and our deviation was 2, then in order to be significant, a data point should lie somewhere well above 7 or well below 3. That'd be 1 standard deviation. So let's say we do this out to 4, which was my average, right? Plus or minus 1. So to be significant, the value ought to be 4 plus or minus 1. So it could be 5, it could be 3, right? It ought to be someplace more or less than that number. Let's look back at the front here. Looking back at the front, we do see some that seem a little bit more significant than others, don't we? Like the Virgos, okay, are less than 4 plus or minus 1. The Scorpio was a little more than 4 plus or minus 1. Okay. So, was my prediction statistically significant? No, I don't really think so. That was 1 there, right? Figured that out. I don't think so. I mean, there were some questions like Scorpio, right? But I think that brings up a bigger point that I think we should kind of talk about here a little bit, okay? And that's especially this question right here. Do you think our sample size was big enough? Did we sample enough different people? Have enough people become president to correspondingly be roughly equal to like population, compared to the United States population? We've had 45 presidents. Is that a good sampling of the population? No, not considering how huge our population is, right? We need to wait a few more million years and maybe we'd have a population sample size that's large enough really to show this. So I don't think in any way our sample size is big enough with just 45 presidents. That should be a major red flag in any scientific study, okay? Are there other variables that we might consider? What things could have affected my bizarro experiment here? Yeah, Jane.
In general, there might just be more people that are born in like October, November.
I love it that you got that. That's awesome. That's exactly what I thought when I sat here and thought about this. So that is really a big deal. Like how, I'll write it down so that you guys can see what I'm saying. Right? If there's more born, better chances that their sign is going to be in there in the president's list. And that can and does really happen. You guys have probably already heard people talking about like that there might be a baby boom after this COVID epidemic is over. Anybody hear that? Yeah. It's a very real thing. So people are cooped up inside and all of a sudden a few months after the pandemic ends, a bunch of babies are born. It's a well-known fact. When I was a kid, there was a huge blizzard, and everybody was trapped inside for days. Like I remember snow was like feet over our door. You couldn't open our door to our house. It was that high. And lo and behold, there were a bunch of babies born shortly after all that, right? So we know that happens. Also, just in any random month of the year, some months maybe more babies are born than others, like just as like a natural occurrence. So There's a lot of things that affect our data here, and it's just kind of cool to lay it all out on paper and see like why science cares about numbers and why they look at statistics and try and see if their numbers really show something, rather than just going, oh look, yeah, I got a result. Okay, like this stuff's important that way. Cool. So like I said, don't sweat over that. We won't do statistical analysis of anything again in here.
Okay, so if you want to have your It's Learning open right now, there's going to be a couple of questions on there. Try and figure out which ones that we're going to kind of be talking about as we go here. They're in the one that's called Lecture Testing Astrology. If you click on that, there's a little document in there with a couple things you can fill out as we go here. We've answered some of this already. Okay. So let's kind of continue here with just what makes up a pseudoscience and why something's a pseudoscience. So, see there? Okay. So what pseudoscience is any body of knowledge that pretends to be scientific, but which fails to comply with the scientific method. Okay. So like one reason that we studied astrology was that there was this belief that these magical planetary rays affected the human body's state of health. And this goofy looking diagram here is actually an original, like way back astrology diagram. And I have no idea what they would look at this diagram to figure out, but apparently like different parts of your body and your health had to do with like different signs and like when you were born and what you're going to have trouble with. I have no idea. But this is like a real legitimate like diagram that an astrologer would use. Interesting stuff. So the Greek root pseudo means false or pretending. So that's where it gets its name here, why we call it pseudoscience. And I want to kind of give you some ideas on how to recognize what a pseudoscience is. Okay? So phrenology, another famous pseudoscience. It's the study of bumps on your head. Have you guys ever heard of that before?
Nope.
No, never went to see the phrenologist? Yeah, so they feel your head, find the bumps, and be like, oh yeah, you're gonna have a problem with your foot tomorrow.
And then you don't.
Right? But maybe you do. I don't know. But definitely not real science, right? Superficially, it appears to be scientific. I mean, look at their diagrams. Look at this head. There's all sorts of little like drawings and like it looks really scientific. So how do you figure this stuff out when you're looking at the mainstream media and you're looking at things online on well, you guys don't probably play on Facebook, but YouTube or something, right? There's all kinds of stuff like this. It's a really fancy diagram. Maybe there's whole papers that look like they've been written. It looks like real science. I mean, it's as good of a diagram as you might have in a science textbook. But obviously, I put this one up there for a reason because most people are going to recognize, yeah, bumps in my head are not going to help you understand the health of the rest of my body, right? Or what's my fate is going to be. But anyway, some things are not as easy to figure out as that. Pseudoscience is usually characterized by vague and exaggerated or untestable claims. Okay? They'll make claims that you really can't test, or they'll be very vague. Like, look at the astrology, all of the statements it made about people like, I don't know, like helpful and loving or kind, or like, this is really vague. Like, sure, everybody is that at one point in time or another, right? So untested claims is a big characteristic. Doesn't follow the scientific method. Okay? Doesn't formulate hypotheses that are testable, that could potentially be falsified. Right? There's not a hypothesis there. Okay? Relies on mythical knowledge rather than logic. If you're looking at something online and it's saying that such and such is true because such and such says it, or because I read it here, or because there is this story about this, like, that's not science. Doesn't make it not useful, but it definitely makes it not science, right? So these are all different characteristics of pseudoscience. You could put down any of these that you want for the question there about what characteristics do you think are the most noticeable about pseudoscience. And I'm going to give you a few more too as we go. So other things we can say about pseudoscience. How can we tell? Like, well, what are the telltale signs? And you can ask yourself which of these you think is the most noticeable, things that you've seen in your life. These vague, exaggerated, untestable claims. Presenting data that supports its claims while suppressing data that would refute them. If you're reading about something online and they only present the data that supports their claims, there's probably a problem there, right? Purposely suppressing data that's going to refute them. Lack of openness to testing by other experts. So if they say things like, you know, these are the facts, and nobody else can test this because they're not qualified to test this because they haven't been trained long enough as an astrologer, right? So not open to being tested by other experts. Lack of progress. Okay. If you look at something and you're looking at it online and you notice that it is the way that it has always been, like astrology or phrenology, they have these ancient texts that they refer to that explain like how this whole thing works, and it never changes. Real science, as you notice, constantly changes. It can be hard for it to change, but my goodness, our theories and our ideas, they keep changing in science because of new information and new stuff that we learn. The coronavirus alone has changed a lot that we know about viruses and we thought we knew. Right? Everything from like how certain amounts of the virus entering your body can make you different levels of sick. Like weird things that like we didn't really recognize about other diseases. So we've learned a lot from that. Personalization of issues. I think this is a big one to me. When I see a group of people talking about something online and they're going on about, well, either you're with them and you believe what they're saying or you don't, and there's just no room for discussion about that, right? You're either with us or against us. That's a pretty good hint that you might be looking at something that's pseudoscientific. But it can be difficult, right? This one is pretty telling too. Using misleading language, like, for instance, scientific sounding words that maybe don't mean that, or don't even have a definition. They just sound sciencey. You can throw an ology on the end of anything, right? It doesn't make it science unless you're actually carrying out hypotheses and tests and experiments, right? You can throw ology on the end of anything. Anything you can come up with, put ology on the end of it, right? Anything at all. So lots of different ways to tell things are pseudoscience, but it still can be difficult. Your best bet is to take a lot of science classes and start to have an understanding of how science works. So what are some things that we can do to tell if something actually is a real science? You're going to notice some things. There's going to be reproducible results. Other people will test it, and if they don't get the same result, it won't be accepted. Interdisciplinary agreement is humongous, right? Humongous. You can't look at anything in astrology and see interdisciplinary agreement with anything in astronomy. And you certainly aren't going to find agreement with geology or biology or psychology. Like, they're not going to agree with each other. And that's a big problem. In the real sciences, one theory, one law has to fit with the rest of the sciences. Otherwise, it's really probably bogus. So interdisciplinary agreement's a biggie. Considering all the evidence, not just what's convenient. Real science doesn't come up with an idea, like they don't decide the Earth is, 4.6 billion years old and then go try and find a way to prove it. Huge misconception. People think that that's how it works. Like, some scientists are sitting around, they're like, hey guys, you know what? I bet the Earth is, 4.6 billion years old. And everybody's like, no way. And they're like, yeah, I'm going to prove it. And they go out and they find the information to prove it. No, they ask a question like, is there a way we can figure out how old the Earth is? And they attempt to, prove that concept wrong, not to prove it right. They say, well, what if the Earth is this old? Can I somehow disprove that? And they set about trying to test it, but not coming up with an idea that they already think is right and then trying to prove it correct, right? It doesn't really work that way. We try to control the bias of the experimenter. It can be difficult, but we do. Okay. versus like astrology, where how the astrologist feels that day might have a big impact on what your sign is telling you. This one I just said, but the experiments aren't done to provide proof of what somebody already believes, but to test a hypothesis. That's a subtle difference, but it's kind of big. You don't just get to come up with a belief, like I believe this, and then try to provide proof for it. Right? We create a hypothesis and see if we can prove it wrong. We actively try to prove it wrong. Okay. And peer review. That's a big one too. We share our results. We review them. A pseudoscience is not going to do that. Right? We've got to publish those things in scientific journals. But it can be tough, right? Lots of pseudoscientific things out there, and now with the internet, you go there and it looks like they've got their own periodicals, their own publishing company, like the whole thing looks very legit. It can be confusing, for sure. But I want to kind of leave off with this last one, the one we talked about already. Just because, like, it's just so poignant to me, is when you're wondering if something is really real science, if you notice that there's interdisciplinary agreement, like you're probably dealing with the real deal. For instance, the impact hypothesis that wiped out the dinosaurs. It seems like a little standalone thing, but it had ramifications across many different disciplines. Right? Paleontologists were able to correlate that no dinosaurs exist beyond 65 million years ago. Like anywhere after that, there's no fossils anywhere 65 million years ago, more recent than 65 million years. Right? Geologists looking for oil, happened to find the impact crater off the coast of the Yucatan Peninsula. Right? That dated to exactly 65 million years ago. Coincidence? Probably not. Definitely not when you go ahead and look at the fact that astronomers studying space rocks that hit Earth, knowing that space rocks are full of things like iridium, which is a very rare element, a radioactive element on Earth, find a layer of that in the rock at exactly 65 million years ago, right? Tack onto that climatologists are able to predict what a big impact would have, the effect it would have on Earth's climate, and of course life, if it landed where we think it landed, and it all fits really, really nicely. Like, that's what gives scientists a warm, fuzzy feeling. One solitary conclusion in one field is not as strong as having a whole bunch of fields agree. So that's a good kind of an indicator, I think, of what pseudoscience or not. But it can be tough, right? It can be really tough. So let me... I think I put that up there.
Okay, let's look at our ideas of the Earth. So, in this first question, who can tell me why the Earth is flat in picture 1, but in picture 2, it's round or spherical? Which of these fit? John, what do you got? D?
Yes.
The Earth is round like a ball, but looks flat because we only see a small part of the ball. Absolutely. Absolutely. Because we're only standing on a tiny little bit here, okay, it looks quite flat where we happen to be standing, but in reality, the whole thing is like a big ball. Like, to us nowadays, because we have satellites, that seems obvious, right? But there's a lot of folks out there, believe me, who think that the Earth has to be like this because that's what they see. If you don't believe me, just look up the flatearthsociety.org. Yeah, talk about pseudoscience. Oh, it's sad. No, don't look at it. Don't give those people any more credence than they already think they have. Number 2, pretend the Earth is glass and you can look through it. Which way would you look in a straight line to see people in countries like China or India? I hear D. D would be a good choice. That's right. Straight on through the Earth to see out the other side. Okay, so these seem pretty obvious so far. Now let's take a look at question number 3. And here's what we're going to do here. Does anybody have an answer to that they want to share? Who wants to draw there what we got? Gavin, give us a drawing there. Draw us what you got there.
I at least think
Yep.
that at the very least, the rock should reach drop downward surface. But considering that they all seem to be standing over water,
Well, don't overthink it. Go a little further in.
potentially also, or potentially also just, you know.
Okay, depending on how deep our oceans are. Oceans aren't quite that deep. That's pretty deep there. Good. So, did anybody happen to draw this? Oops.
What?
Yeah, I mean, don't be embarrassed. I've seen, over the course of my career, I have seen this drawing at least once every 2 years. Right? It's okay if you did that, but I want you to see your misconception that what Gavin just did is way more correct.
Because gravity.
Because gravity, this is a spherical object, each of these people dropping this ball, it's going to fall towards the surface of the Earth. Now, maybe you've never stopped and considered the fact that there are people on the planet down here on the bottom, and if you could see them through the clear Earth, they'd be standing upside down to you. Like, if you could look through the planet, you'd be looking at their feet. Be really messed up, wouldn't it? It would really, really be messed up. But that is absolutely the case.
Wow.
But because of the way gravity works, these objects are all going to fall down to the ground. Okay. Now let's see if we can go another step further. We're going to take a look at this one. I'm going to move it out of the way here for a second. And let's see what you guys can come up with. Let's draw a couple of these. We can put a little hole in it. So there's a hole that goes all the way through the Earth, out the other side. Neglect the fact that gravity would smash that thing back together in a heartbeat. We couldn't drill a hole like that. But let's see who can come up with the best explanation of what's going to happen when we drop a rock from that side of the Earth. What's it going to do? Draw one on there for me, Gavin. What do you think it's going to do?
Wow.
Your little guy there. Yo. That is a funny looking guy I just made. Drop a little rock. Anybody else have a thought? Let's see what we can come up with here. Hoping we'll have a couple different options.
Anyone else? Anyone? Still another one.
Anybody else have a different idea? Oh, we have two of the same ideas so far, huh? Awesome. Yeah, don't be afraid. It's cool. It's okay to be wrong. It's totally fine. There's different levels of correct too, because we can go different directions with this. So this is a typical one where the person drops the rock, and it goes all the way down and clear on out the other side. Okay. It's easy to think that, but you've got to wonder. Remember, there could be a person over here. What happens if they drop a rock? Right? So this really wouldn't happen. And we have a couple of other ones up here that have been drawn that is really pretty good here. We've got it falling, going almost a little bit near the center and kind of wiggling back and forth and going in like that. I think we could probably do even better though. Think about the momentum, if you've had physics, that this rock's going to have if you drop it from this height due to gravity. How much potential energy does that thing have, and how much kinetic energy is it going to have as it goes down? What's it really going to do? You're right, it's probably going all the way down. almost right back again to where that guy was standing. And then what's it doing? It's going back up. Well, up to the guy on the surface up there. And each time it oscillates,
Oh my gosh, it's just gonna get.
if we want to get really technical, each time it oscillates, if there's some friction in there with the atmosphere, if there's air in there, which we're assuming there is, I suppose, it's probably going to slow down, isn't it? So over time, I think you guys are absolutely right. It's going to gradually come to rest right there in the center of the Earth, and it's going to stop right there. But it's going to go back and forth a bit. And if there was a guy over here or a girl over here, she could catch it. Hold on to it for a second, because it's going to be going really slow by the time it gets to right here. Let go of it again and send her on back.
So far, I think air friction would keep it from coming out the other end.
Probably. More than likely, it wouldn't make it quite that far if there's friction with the air, I would have to say. But irregardless, like, it's a good thought experiment. A lot of the things that people like Einstein and Newton came up with were thought experiments. They're like, what if something ridiculous, like I could split the Earth in half and drop a ball? What if I could actually go fast enough to ride along on a beam of light? Right? It's these ridiculous ideas of like pushing the boundaries of what's possible, even if it could never be possible. Like, what would happen? And a lot of new science comes from stuff like that. So yeah, this is most likely what would happen, is it would go back and forth until it came to rest there in the middle. Interesting, right? So
Let's see if we can prove some of this. Like I said, there are a lot of goofy people in the world. People get duped pretty easily. We like conspiracy theories. We like weird stuff that seems like it shouldn't be true, right? And there are loads of folks who think the Earth is still flat. And how you can possibly think that in today's day and age, when you can literally watch a video from the space station, like on board, like you're there, right? But there's people who think we haven't been to the moon either, even though we've returned literally tons of rocks from the moon. We've got rovers driving around on Mars. I'm not sure how they explain that. But let's see, how do we know that the Earth is not flat? Well, there's actually a number of ways. Even ancient people knew this. I don't know why in today's society we feel the desire sometimes to revert what we already know and have proven over and over again, but we do. One way that we know that the Earth is actually not flat, I'll give you some ammunition against people who think the Earth is flat here, okay, is that if you watch a boat coming in over the horizon, the ancient Greeks knew this, the first part of the boat you see, if it's coming from out to sea, way out at sea, is the mast. And slowly, the boat doesn't just kind of get bigger and bigger. The boat literally looks like it rises up out of the ocean. It like just lifts up out of the sea because the Earth curves. So as they come over the curvature, it's actually, you can see far enough on the ocean, especially with a pair of binoculars, that you can see the curvature of the Earth if you're looking at a boat out there. That's wild, isn't it? So you can actually see it as it comes in over the horizon. And the ancient Greeks knew this. Another one, we could climb a tower and look for light pollution from Tokyo. How about that? If the Earth were flat, you ought to be able to see from any tower here on Earth. If you climbed up high enough, you ought to see Tokyo lit up at night. Isn't that a weird thought? But you can't, because the Earth is not flat. But if it were, you could get up high enough that you could see over all the trees and everything else, and you would physically see Tokyo like a bright light in the sky lit up in the distant horizon. But we don't see that. So we can also say the Earth is not flat. Of course, we could always just look at any photo or video from the International Space Station.
There's always going to be people who say that it's CGI.
Yeah, so it's just CGI.
Solid concrete evidence.
It's pretty crazy that you can see like the cities that are lit up there. I think those are lightning flashes that are going on. Like, it's pretty cool. And if you look really close on the far right, you see one of the panels from the space station over there in dark, in relief. But that's obviously some sort of a time-lapse thing that they did. But there's loads of stuff like that that you could look at. Right? How about this one? This is one that I always wonder about how people explain this away. If you watch a lunar eclipse, you can actually see the shadow of Earth. and it's not flat, it's curved. So if you're looking at an eclipse, a lunar eclipse, you are literally watching the shadow of the Earth pass over the moon. I'm not sure how the flat earthers explain this, because it's curved. It's crazy the amount of evidence that we've got here that people don't accept. Right? And the last one that I'm going to talk about, that we're going to do a little activity on, is a very, very famous one, is we could measure some shadows. This is a famous well in Syene, and this was a famous part of a famous experiment that was done to determine the circumference of our planet. Crazy, right? So in Syene, there's a well, and at noon, on the longest day of the year, the sun was directly overhead and made a perfect, like illuminated the bottom of this really scummy looking well, some green slime growing in there. I wouldn't want to drink that water. So that there were no shadows anywhere on the edges of it. Okay, this was well known to these ancient people. And so what they did was they found a post in Alexandria that was a known distance away, and they measured the angle of that shadow. And using nothing more than geometry, we're able to calculate the circumference of the Earth all the way around. So we're going to see if we can pull that off here, okay? Okay, so take out your paper. Says called Measuring Earth's Circumference, and it talks about a guy named Eratosthenes, who figured this all out in 240 BC. Woo.
Okay, there's going to be a little quiz over this when we're done. So if you pay attention, you're going to understand the math, and it's actually really easy math. Okay, but it's the concepts that I want you to get. Okay, so in about 300 BCE, actually about 240 BCE, this guy by the name of Eratosthenes, who was a librarian in Alexandria, Egypt, discovered how to measure the circumference of Earth. It's honestly one of the most outstanding achievements of ancient science. So only about 50 years after Aristotle described evidence that supported the idea the Earth is shaped like a sphere, this guy Eratosthenes figured out how to measure the thing's circumference. So in this activity, we're going to discover like how he actually did this, what his reasoning was, and we're going to use only the evidence that he had available to him to try and calculate it ourselves and see how we kind of come up with this. Okay, there's two pieces of information you kind of have to understand. And first is, and I'll show you how this works out, the angle of a shadow formed by a stick can be measured as a fraction of a circle. So you can measure the angle that a stick makes as a fraction of a circle. I think I've got a picture on here somewhere of that. I do, there we go. So there's the stick. We can measure this angle as a fraction of a circle, like if that whole thing was a circle. Okay. And another object that you're gonna have to know is a geometry thing that Eratosthenes knew, is that parallel lines cut by a straight line create equal angles. So check this out. I did it on the back here. Here's some parallel lines cut by a straight line will create equal angles. And you did this in geometry class. I guarantee, if you've had geometry, you did this. You get equal angles when you cut across two parallel lines. Okay, this is all he needed to know. Now, you're thinking, oh, the guy was just a librarian, but librarians are really important people today, but back in the day in ancient Alexandria, like being a librarian was basically being like the smartest person in town. Like you were imagine how smart you'd have to be given a job where you don't have to go do any toiling in the fields. You just hang out in the library and help people learn things and understand things. Like he probably was incredibly, I mean, he had to be an incredibly intelligent individual to come up with all this. So, famous Greek scientist librarian read that at noon on the longest day of the year, the sun's light shines directly down a well in the city of Syene, which is modern day Aswan, I think, located 700 miles to the south of where he lived in Alexandria, Egypt. However, at noon on the same day of the year in Alexandria, a vertical post casts a shadow that's 1/8 the length of the post. So he's got this stick in the ground in Alexandria, and there's this well in Syene that the whole bottom of it illuminates on this specific day of the year. So he had to wait till this day happened, like exactly, to make this measurement. And he measured the angle here that came from this stick. Okay, so let's take a look here. What I want to draw is the sun in here to show where it would have to be in order to shine directly down the well at noon and in Syene, and then create a shadow in Alexandria. So first of all, realize I can only get the sun so far away. So we're going to draw this sun up here, my third grade example of the sun. Woo, look at that. Happy sun. In order to understand this, you've got to understand that the sun is so far away. This wouldn't work if the sun was close like I drew in the picture. The sun is so far away that any ray of light coming from the sun is actually parallel to any other ray of light. So they don't diverge at angles. The sun's not that, it's so far away that it's like a point source. They come parallel to each other. So just to show you kind of how that works, this is what it would look like if these rays were coming from the sun like this. Magical rays of sunshine. Okay, see all these magical rays of sunshine here? Notice how some of them, because the earth curves, are going to cast a shadow over here, but they're going to go straight down the bottom of that well. Okay, this would not work with a light source that's nearby. This only works because the sun is so far away that it's like a little point in the sky. Okay, it's like a point source. Otherwise, it wouldn't work. So the rays of sunlight are parallel. So what that's going to cause to happen here, and we're going to see in a second, is if we were to trace out this ray of light right here, it's going to go like this. This ray of light that goes down this well, if we continued its path, which we can't like through the earth, is going to go like that. This stick that's stuck in the ground has an angle that goes like this. Check out what we just did. We just created two parallel sun rays and a line that cuts across them. The angles are going to be equal, aren't they? If you know one angle, you know the other angle. Because what Eratosthenes wanted to know is what's the distance all the way around the planet. So he had to figure out what angle was here and figure out what the distance was between these 2 points. Okay, so what I said here was, why do we see a shadow cast by the post at noon in Alexandria at the same time we see no shadow in Syene? If the earth were flat, how would the shadows appear differently in the two locations at the same time of day? So let's think about this. The sun if we were looking at in Alexandria, the sun's not going to be it's not directly overhead in Alexandria, because Alexandria is 493 miles south, because Earth's surface is curved. So these people over here don't see the sun directly overhead, but these people here see the sun sitting right over top of their head because the earth is curved like that. Okay. Now, what if the earth was flat? What would happen if the earth was flat? What would you see? The shadows would be exactly the same. Fantastic. There'd either be no shadows or they'd be the same. All shadows All the shadows would be the same length. Let's do a little demo of that. So if I had a globe, which I happen to have, I'm not going to actually hit Egypt here. I'm going to pretend we'll go far away so we can make it. Just so happen to have a flashlight too. How about that? Field trip. Let's see if I can make this happen. So if you're directly overhead in one of these shadows, one stick is going to have no shadow. Okay, if I'm directly overhead, but the other stick, if I come around to this side, is going to throw a really big shadow because that Earth is curved like that. So when one of these had no shadow at all, Eratosthenes knew if he just knew the distance from here to the other point and knew the angle of that shadow, he could figure out how far it was going to be around the whole planet. It's a pretty slick trick. So let's see how he did it here. Okay. On noon, the longest day of the year in Alexandria, the length of the shadow cast by the post was about 1/8, is the thing you're going to need to know. 1/8 the length of the post. Using geometry, Eratosthenes found that the angle at the top of the post must have been about 1/50th of a circle. Okay, so knowing that this was 1/8, he figured out with some geometry this was 1/50th. So if you drew an imaginary circle here, it would this was 1/50th, this angle right here, which meant that this angle down here was also going to be 1/50th. So let's flip this over and take a look here. Like I just said, if we draw two parallel lines with a line that crosses them, corresponding angles are equal. For instance, A is equal to E. Oops, you can't see. A is equal to E, right? That's exactly the situation that he just pulled off. So since the sun is very far away, a ray of light, of sunlight that reaches Alexandria is parallel to a ray of light that reaches Syene. Eratosthenes realized that the angle of the shadows cast by the vertical post in Alexandria equals an imaginary angle formed by the center of the Earth, Alexandria, and Syene. Since that angle was 1/50th of a circle, the distance between Alexandria and Syene must be 1/50th of the distance around Earth. Boom. Okay, there's a picture of it again there. There's the sun. Okay, here's the line that crosses these two lines. If I continue these lines, okay, crosses that. This angle equals this angle. If this angle is 1/50th, then he's 1/50th. So Eratosthenes, being lazy or wealthy or whatever he was, paid somebody to measure the distance from Syene to Alexandria, because the only way you could do it was to walk it and count your steps. It's like, talk about a long ways, okay? So this person walked and counted their steps, and the distance they measured was 4,400 stadia, which today we think was about 493 miles. Nobody really knows, because the Greek measurement of a stadia was based, I guess, kind of on how long their stadiums were, where they would hold the big, games and whatnot. So nobody's really certain, but we think it was about this far in modern measurements. So we're going to try and use those, okay? See if we can calculate the circumference of the Earth, and we'll see if we can show our work. So what are you going to do? You know that it's 793. We're going to do this in kilometers. Kilometers from here to here is 793 kilometers. Okay. And we know that that's 1/50th of the way around the planet. What would you do with those numbers? It's not complicated math. That's the equation right there. That's how complicated it is. So let's see how far it was. 50 times 793 That's how many kilometers. Can you see that? There you go. So, by modern measurements, the circumference has been measured to be right here. How much was he off by? Well, let's just do a little subtraction here. Oh, I guess we'll finish this later. We'll finish this next time, guys. I'll put my video up. We'll do a little quiz over it. I'm going to keep working out my math here so that everybody at home can see it. He was only off by 424 kilometers. Now, that could have been luck. It could have been the real deal, but he wasn't off by much, was he? If we work out the percentage error here with the formula right here, we would take or take our estimated value, which is what he estimated, with our accepted value, which is our modern accepted value, and then we're going to divide by the accepted value, which is again the same. Okay, and we take all that, multiply it by 100, okay, to make a percent, and then we're going to get, when you do all that, only 1% error. That's phenomenal. Like, we almost have to think that some of that had to be luck, right? But it really is. He was that close to exactly the accepted measurement that we have today, which is pretty stunning considering he just paid a dude to walk across, took a measurement from a shadow here, took a measurement from a well here, sorted it out with some geometry. Yay, geometry. You should have enough info now to do your quiz. Just think it through, and you'll have some numbers that are pretty similar. Remember, the numbers that were important here were the distance between the two, between the shadow post and between the well, and the distance, the knowing that you're 1/50th, okay? And all we did was multiply those two numbers together to get our answer, because you're going to have to do that on the quiz. Cool.